Good morning, class. Today we are going to talk about multiple regression, and the main purpose of this video is to give you a worked example of how you can approach a multiple regression problem and decide which variables to include in your model and which ones to exclude. So for this lecture today, I've created a data frame that consists of blood pressure values from a published study, and the question was whether the blood pressure values of a child are influenced by those or correlated with those of their mother and father. And I've also put in a fourth variable here, which I called elevation, which is just completely made up fake numbers representing height above sea level. And I'm putting that in here intentionally as a variable that should not be correlated with anything, because there's no reason to think that even if there is a reason to think that your elevation is related to your blood pressure, certainly it will not be in this case, since I've just made up the data at random. Okay, so there's just 20 data points in 20 observations in this data. So I have lines 1 through 4 to read in the data, and then line 6 builds the data frame. Okay, and so if we look at the data frame now, which I've called data, we see here down in the console that we have values for mother, father, child, and elevation. Okay, and there are 20 observations. Okay, so a regression model. The first model I'm going to run is going to look at the value for child as a function of mother, father, and elevation. So starting with putting all variables in the model. And that's line 8, and then line 10 is the summary of that model. Okay, so let's take a look at that. So we see that the blood pressure is positively related to both the mother and the father's value, and also positively related to elevation, but by a very tiny amount, an amount that's essentially 0, so very close to not being related. And we can interpret that more clearly by looking at the p-values for each of the variables. So we see for mother it's 0.03, which is significant. For father it's 0.01, which is significant. And for elevation it's 0.21, which is not significant. Okay, so this all sort of makes sense. Your blood pressure is influenced by your parents, but not by your height above sea level. If we look at the R-squared for this model, we see that it is, we can look at the adjusted R-squared. And as you recall, I earlier talked about the difference between the multiple R-squared and the adjusted R-squared, and how they tend to be extremely similar. That's true when you have large samples. So here our sample size is only 20, and I think, in my experience, to have a sample size of 20 for this type of study would be highly unusual. You would likely have hundreds or thousands of subjects here. So this is sort of a made-up example for the purposes of illustrating the concept. So when you have a small sample, your multiple R-squared and your adjusted R-squared can actually differ by a fair amount. But anyway, let's just keep our eyes on the adjusted R-squared for now, which is 0.57. Okay, so we might say, well, let's throw out elevation from our model and build a new model with just mother and father. Okay, and I'm calling that model 2. So I run that, and we see that the p-values for mother and father remain significant. They're actually more significant than they were before. Not by much, but the p-values are actually smaller. And so the ways that these model parameters change as you add or subtract model elements, as you add or subtract variables, is fairly complicated and often difficult to predict. And that's because variables interact with each other in complicated ways. So it's not obvious to me how to interpret the fact that the p-values actually got a little bit smaller once we took out elevation. But we typically don't worry about that too much. We're just concerned with the fact that they remain significant according to our standard of 0.05. Now, if we look at the adjusted R-squared for this model, we see that it's 0.55, so it's actually gone down. So you might say, well, even though elevation wasn't significant, it did improve the R-squared by a little bit. It raised it from 0.55 to 0.57, and that's true. And so when we're deciding which variables to include or not include in a model, we're not trying to maximize R-squared necessarily. We're trying to look for the point where the R-squared ceases to grow by very much. Because even a poorly fitted variable like elevation will often still provide a little bit of explanatory power. And so the more variables you put in, the R-squared will go up a little bit, typically. It won't go down. So the more variables you put in, adjusted R-squared will go up. But the question is, does it go up by an amount that matters? And in this case, it went from 0.55 to 0.57, and I'm saying that that is a pretty small change, and so we would ignore that in this case. Now, in fact, there are sophisticated statistical tests that exist, which we're not going to cover in this course, which can answer this question more officially, so you don't have to be left with trying to decide subjectively if 0.57 is enough of a change from 0.55 to include it in your model. But we don't have enough time in this course to get to that level, so for the purposes of this course, if the adjusted R-squared only changes by a small amount and the p-value of the additional variable is not significant, we want to take that variable out of our model. We can look at mother and father each on their own, and that's what models 3 and models 4 do. So first I'll run model 3, which is just mother on its own, and so we see that the mother variable is significant. R-squared is 0.30, much lower than 0.55. So if you just stopped at mother, that would not be a good choice because you're missing a lot of important information which is coming from the father variable, and likewise model 4 is only containing father. We see the R-squared is 0.26. Father is significant on its own, but again, well below 0.55. So with mother and father on their own, you get values between 0.25 and 0.30. When you add mother and father together, it jumps up to 0.55. And when you add the made-up variable elevation, it only jumps up to 0.57, so we would choose as our final model, model 2, which is mother and father. So this video should help you with one of the homework problems that is similar in nature to this explanation. Thank you for your attention.